The subtraction principle of counting says that if you want to count all the elements in a set that don't have a certain property, you could count all the elements in the set and then subtract the ones that do have that property. Let's look at a more advanced version of this idea. Let's suppose we want the cardinality of A union B union C, where these are all sets. And we have cardinalities of intersections. Let's draw a picture of this. So we want the union. So we could count everything in A, and then count everything in B, and then count everything in C. Of course, we do that, we're overcounting because we counted the things that are in A and B twice. Once when we thought of them as elements in A, and again when we thought of them as elements in B. So we could then subtract all the elements in A and B, and similarly subtract all the elements in A and C, and subtract all the elements in B and C. But that's not quite right either, because we considered the elements that are in A, B, and C simultaneously too many times. So we could add back those elements and let's see what we get. So we've counted everything in A. In this section, we've counted everything once. In this section, we've counted everything once because we counted it twice and subtracted once. In this section, we've counted everything once, once, once. And in here, we've got 4 plus signs and 3 minus signs. So we've counted everything there once, too. So we've counted everything once, exactly once, in the set that we want, A union B union C. So apparently, the number of elements in A union B union C is number of elements in A plus number of elements in B plus number of elements in C minus number of elements in A and B simultaneously minus number of elements in A and C minus number of elements in A and B plus number of elements in A and B and C simultaneously. In general, if A1 through AN are subsets of some set T, then the cardinality of the union of the sets is equal to a sum over subsets of 1 through n, negative 1 to the cardinality of that subset plus 1 times the intersection of sets indexed by that subset A I. So we start off with all one element subsets with a positive sign, and then two element subsets, single subsets with a positive sign, intersections of two subsets with a minus sign. Now the two element set is the two indices of two different sets. So AI, AJ, and then plus intersections 3 at a time, and that corresponds to subsets S with 3 elements, I, J, and K, say. Now let's suppose that we want not the union, but the complement of the union. Everything that is outside of this diagram. Well, if we know how to count the things that are inside this diagram, we could just take the cardinality of our universe set T and subtract that. So this is just number of elements in T minus the number of elements in A union B union C. So that looks like a trivial extension of what we just did, but in practice it looks a little bit different. So in practice, this principle looks different. It looks something like, let's let 1 through n be a list of n flaws. Then the number of flawless elements in T is, so number of elements in T minus a sum over I number of elements with flaw I. Now that means with flaw I at least, because having flaw I doesn't prevent an element from also having flaw J, flaw K, other flaws. So then we have to add back in the sum over pairs I and J, number of elements with flaws I and J, again at least. But the element with having flaw I and J might have flaws I, J, and K, in which case we'd add it in 3 times because it has flaws I and J, and flaws I and K, and flaws J and K. So minus the sum over I less than J less than K, number of elements with flaws I, J, K, at least, etc. So in general, for each subset S of flaws, let's define B of S to be the number of elements having flaws S at least. Then the number of flawless elements is a sum over all subsets S of n -1 to the cardinality of S times B of S, the number of elements having precisely those flaws. So let's look at an example. Let's ask how many rearrangements of the word 1, 1, 2, 2, 3, 3 up to NN have no repeated letters, no consecutive repeated letters. So this is the total number of rearrangements minus a sum over I, the number of arrangements with I at least, plus a sum over I less than j, the number of rearrangements with I and jj at least, etc. All right, so let's start counting these things. The total number of rearrangements is, well, we've got 2n letters here. So 2n factorial ways of rearranging them, except that would be overcounting because we've got 2 1s, 2 2s, 2 3s. So we better divide by 2 times 2 times 2. We better divide by 2 to the n. All right, minus n choose 1. This is a number of ways of choosing one letter to appear consecutively. That times the number of rearrangements of, let's say, 1 1 comma 2 comma 2 comma 3 comma 3, etc. So I'm going to treat 1 1 as a single letter since we've got one letter to appear consecutively, so might as well say it's 1. It doesn't make any difference which one it is. So now we've got, instead of 2n letters, we've got 2n minus 1 letter because those ones got combined to make a single letter. So there's going to be 2n minus 1 letters to permute, and then we'd be overcounting because of the 2 2s, 2 3s, etc. So there is n minus 1 letters that aren't necessarily appearing consecutively, that we could swap and not get different words. So there's 2 to the n minus 1 corrections we have to make there. So then we'd add plus n choose 2. Now there's 2 letters that were going to appear consecutively, say the i's and the j's, times the number of rearrangements of 1 1 comma 2 2 comma 3 3 4 4, etc. And the number of those is, let's see, we had 2n letters minus 1 minus 2. So 2n minus 2 letters now. 2n minus 2 factorial, and we have to divide by the correction factor of 2 times 2 times 2 for 3 up to n. So that's 2 to the n minus 2. And then we can see that if we're thinking that p letters are going to appear with consecutively, the two of them, then we'll have n choose p ways to figure out which p letters are appearing in the pairs, and then we'll have n minus 2n minus p letters here to permute, and then 2 to the n minus p correction factor for all of the pairs of letters that are still separate that could be swapped. So that means that we get let's see, maybe I could combine this into a sum. So n choose 0 is 1, so that could be a coefficient there. 2n minus 0 over 2 to the n minus 0. So this actually matches the same pattern as the others. It's just with 0. So we've got a sum as I goes from 0 to n, 2n minus I factorial over 2 to the n minus I, and the sign is negative 1 to the I. The 0th power gets a, when I is 0 we've got plus, when I is 1 we've got minus, when I is 2 we've got plus. Now this isn't a fantastic formula. Well, one thing that's not fantastic is it's a sum rather than an explicit formula. Another thing that's not fantastic is it has minus signs in it. Now we can tell right by the question that the answer is going to be positive. How many rearrangements are there that have a certain property? So it's obviously going to be a positive number, or at the very least non-negative. So it's slightly disappointing to have minus signs in the sum if we're describing a positive number. But in this case, I think that's the best we can do. And sometimes we just have to settle for that. The end.